So right now we're going to talk about specific heat capacity. So in our last video we talked about how just normal heat capacity refers to the amount of heat needed to increase the temperature of the whole object, and we compared the bathtub of water versus the cup of water. Specific heat, which has a symbol of a capital C, is the amount of heat it takes to raise the temperature of only 1 gram of the substance. So not the entire object, just 1 gram of it by 1 degree Celsius. And oftentimes we just call it specific heat. And water has a humongous value compared to other chemicals. For water, the specific heat of water is 4.184 joules per grams degrees Celsius. And so that means for water, it takes a long time to heat up compared to other things, as well as a long time to cool down. And so one way that I like to think about it as an analogy is imagine that you have 2 cars. Okay, the first car that you have is a Hummer, and the second car you have also starts with an H, but is a little different. It's a Honda. Now, if you have both a Hummer and a Honda, and they're in a race, and they both have 10 gallons of gas, okay, and the way to win the race is to see who can drive the farthest. Well, we know both, let's say they're starting out at our start line, okay, and the markers are at the miles. So 1 mile, 2 miles, 3 miles, which my miles are not evenly spread, but you know what I mean. We could look up the fuel efficiency for each, the Hummer and the Honda, and we could find out how many gallons of gas it is per mile. And so we could say, okay, let's say the Hummer takes an entire gallon to go 1 mile. Well, that means he'll only be able to go 10 miles because he has 10 gallons. But if the Honda only uses 0.1 gallons every time it goes a mile, it will be able to go 10 times further than the Hummer. Okay? And so I'm sure you're asking, Ms. Nichols, what does this have to do with specific heat? Well, we can use a similar analogy, but instead of cars, we have substances. So let's say I have a substance and it's water, and I have another substance and it is mercury. Okay, these two are often compared in this type of compound. Now, the water has a specific heat equal to 4.184 joules per grams degrees Celsius, whereas mercury has a specific heat of 0.14 joules per grams degrees Celsius. And so that means if they both start out at 0 degrees Celsius, okay, that means in order to go up by 1 degree, water is going to have to use or gain 4.184 joules. In order to go to a second degree, water will need to gain an additional 4.184 joules of heat or energy. However, mercury only needs to use 0.14 joules. And so this is why if you had mercury and water sitting in the sun, receiving the same amount of energy from the sun, the mercury will actually heat up to a higher temperature, okay, because it's going to change. This is also why if you go to the beach, let's say this is the beach, you have the water, you've got a palm tree, and it is just, you're at the beach, you're having a good time. If you walk in the water, the part of the beach that's on the water, your feet are going to feel cool, right? And the sand will not burn your feet. But if you walk on this part of the beach that doesn't touch the water, the sand is so hot that it feels like fire on your toes. That's because the sand has a smaller specific heat than water. It's going to heat up much faster, whereas water is going to take a long time to heat up. Okay, so those are my two kind of pictures for that. And so if we look at how we can calculate specific heat, or what we use it for, we use specific heat to calculate the amount of heat required to change that whole object, depending on how much of it we have. And that formula is Q equals mc delta T. The triangle is the Greek word delta, or the Greek letter delta, and that means change in. So you could have delta E, and that's change in energy, or delta Q is change in heat, or delta T is going to be our change in temperature, which is measured in degrees Celsius. And it is calculated by T final, so our final temperature minus our initial temperature. And Q is our heat, and it's measured in joules, represented by the J. M is our mass, which is measured in grams, represented by the G. And C is our specific heat. And we can use this in calculations like in example problems 1 and 2. So in example 1, it says it takes 487.5 joules of energy. Well, as soon as I see that letter J for joules, I know that this is Q. So I'm going to write Q is equal to 487.5 joules, because it's important to just kind of know exactly what we have. And it says we need that to heat 25 grams. Well, I know that grams, it measures our mass of something. So M is equal to 25.0 grams. And it's heating it from 25 degrees Celsius to 75 degrees Celsius. Well, that means those are temperatures. So 75 degrees is going to be our final temperature, so TF, whereas 25 is our initial temperature, which means when we calculate our delta T is our final temperature minus our initial temperature. So that would be 75 degrees Celsius minus 25 degrees Celsius, which will give us 50 degrees Celsius. And they want to know what is the specific heat. Well, the symbol for specific heat is C, so I'm going to put a question mark next to that because we do not know. Now, because I see temperature and I see the word specific heat, that tells us that we need to use the formula Q equals mc delta T. Our other formula, which is Q equals m times delta H, does not have temperature and it does not have specific heat in it. We cannot use it for this problem. And so once I've written my formula, I'm going to plug in my numbers. So Q is equal to 487.5 joules. Our mass is 25.0 grams. We do not know C, so I'm going to leave it alone. And our change in temperature is 50 degrees Celsius. So I'm going to first simplify the right side of the equation. So 25 times 50 is going to give us 1,250. Now I multiplied grams times degrees Celsius, so I'm just going to leave them side by side, and I'm going to put them in parentheses with the C outside of it. So I did not touch the specific heat, so it just kind of stays on the outside. And I did not touch the left side of my equation, so it stays the same. And remember, in order to move a number from one side of the equal sign to the other, you have to do the opposite of the math. So 1,250 grams times degrees Celsius is being multiplied by our specific heat. That means we divide on both sides in order to move it. so we divide. So on this side, it will cancel out, and you will get C is equal to 487.5 divided by 1,250, and you get 0.39 joules over grams degrees Celsius, because none of our units cancel out, so I write it exactly how I saw it. And that is my answer. Okay, now in question number 2, it says how many joules of heat are needed to raise the temperature. So they're asking again, how many joules? So they want to know Q are needed to raise the temperature of 10 grams. So Q is our question mark. M is going to be 10 grams from 22 degrees Celsius to 55 degrees Celsius. So those are temperatures. So my delta T is 55 degrees minus 22 degrees, which gives us 33 degrees Celsius. And they tell us the specific heat, so C is equal to 0.90 joules per grams degrees Celsius. So the very first thing we do is we write our formula now that we've labeled everything. So we label Q equal to MC delta T, and we plug in the numbers that we have. We know that Q is equal, well, we don't know Q, so I write it again. Our mass is 10.0 grams. Our specific heat is 0.90 joules per grams degrees Celsius. And our delta T is 33 degrees Celsius. So here we see that I'm going to have several units cancel out. My grams will cancel out with grams, Celsius with Celsius. So that means only joules will be left. And we multiply our numbers. So 10 times 0.90 times 33 will give us 297 joules. And that would be the amount of heat needed to raise the temperature. And so we can do all of these practice problems, and there are several problems on the back of your packet that you can work on to practice this type of calculation.